Picture this: you're standing at the edge of a colossal wall of ice, so immense it seems to hold up the sky itself. All around you is a landscape of breathtaking silence and deep, ancient cold. But this isn't just ice, it's a library, a frozen archive holding secrets from hundreds of thousands of winters ago. Trapped within these towering cliffs are tiny, delicate bubbles of air, preserved perfectly across countless millennia. They carry echoes of ancient atmospheres, whispers from a world long gone, waiting patiently for someone to listen. This isn't science fiction, it's real. These formations are known as atmospheric fossils, and they are among the most extraordinary records of Earth's climate history ever discovered. In this video, we're embarking on a journey to uncover the mysteries of what many call the frozen cliffs that captured the sky. We'll explore how something as simple as falling snow, layer by delicate layer, can become a time capsule preserving the very air our planet breathed during ice ages, warm periods, and moments of profound change. We'll dig into the science of how these icy vaults form, how researchers extract their priceless data, and what these fragile bubbles tell us not just about where we've been, but where we're headed. This is a story written in frost and sealed by time, and it has never been more urgent to understand. From groundbreaking discoveries hidden deep within Antarctic ice to the startling ways these records are reshaping modern climate science, we'll uncover how atmospheric fossils help us decode Earth's past and illuminate its future. You'll see why these frozen giants matter, not just to scientists, but to every one of us living on this rapidly changing planet. So settle in, open your imagination, and get ready to travel through time, ice, and air with us. The secrets of a million winters are finally ready to be heard. To understand the incredible power of these frozen archives, we have to travel back in time to Earth's great ice ages, when vast sheets of ice began their slow, patient work. Picture a relentless winter in a place like Antarctica or the heart of Greenland, where snow falls year after year, century after century, but it never truly melts away. Each new snowfall buries the one before it, and over immense stretches of time, the weight of countless layers begins to press down. The delicate, crystalline snowflakes at the bottom are gradually compressed, their intricate shapes collapsing and merging. They first transition into a granular, porous material called firn, an intermediate state that looks like coarse sugar, and eventually, under the immense pressure of hundreds of meters of accumulation, they are squeezed into solid, dense ice. This transformation is where the magic happens. As the snow compresses, the tiny pockets of air that were trapped between the flakes don't just vanish. They become sealed off from the outside world, imprisoned within the ice itself. Each one of these microscopic bubbles is a perfect, uncontaminated sample of the ancient atmosphere from the very year it was trapped. It's like nature's own method of scientific sampling, creating a flawless time capsule that preserves the exact chemical composition of the air, including the levels of carbon dioxide, methane, and other greenhouse gases at a specific moment in Earth's deep history. These bubbles are not just curiosities, they are direct snapshots, allowing scientists to analyze the planet's breathing patterns across hundreds of thousands of years. The polar regions are the undisputed guardians of these priceless records for a crucial reason: their profoundly stable and cold environments. The consistent sub-zero temperatures prevent the ice from experiencing significant melting or thawing cycles that would distort the layers or allow the trapped gases to escape or mix. This stability is paramount. As one glaciologist famously noted, the ice sheets in Antarctica act like a climate tape recorder that has been running continuously for nearly 1 million years, offering an unbroken, year-by-year chronicle that is simply unavailable anywhere else on Earth. No tree ring, sediment layer, or coral reef can provide such a direct and detailed measure of the ancient atmosphere. What makes these atmospheric fossils truly unparalleled is the sheer continuity and length of the record they hold. While other natural archives might offer glimpses or snippets of past climate, the deep ice cores extracted from these frozen cliffs present a continuous timeline. By drilling down through the ice, scientists can literally traverse time, moving backwards through millennia with every meter of core retrieved. The deepest layers hold the oldest air, allowing researchers to reconstruct a year-by-year diary of Earth's climate history, revealing not just gradual shifts but also sudden, dramatic events like volcanic eruptions or interstellar dust falls that were captured in the snowfall of a single season. This foundational process, snow turning to ice, trapping air, and preserving it in a stable deep freeze, is why these cliffs are considered one of the most invaluable libraries on our planet, holding the raw data that has fundamentally reshaped our understanding of climate change. Among the most groundbreaking chapters in this story of discovery unfolded in the stark, pristine expanse of Antarctica. It was here, at remote stations like Vostok and Dome Sea, that international teams of scientists embarked on an audacious mission to drill down through the ice sheet and pull up a continuous record of Earth's past. The conditions were almost unimaginably harsh. Temperatures could plunge to -80 degrees Fahrenheit, where a single exposed patch of skin would freeze in seconds, and machinery became brittle and prone to failure. Yet, driven by a powerful scientific curiosity, these researchers persevered, establishing deep field camps that operated for years at a time. Their goal was to extract pristine ice cores, long, cylindrical columns of ice that, when carefully analyzed, would read like the pages of a history book written in frozen air. The process of extraction itself is a monumental feat of engineering and endurance. Imagine a massive drill, specially designed to operate in extreme cold, slowly and meticulously boring down into the ice. It's not a rapid process. Retrieving a core that spans hundreds of thousands of years requires incredible patience, sometimes taking multiple field seasons to reach the deepest, oldest layers. Each segment of ice, typically about 3 meters long as it's brought to the surface, is handled with the care of a priceless artifact. Scientists and technicians, working in unheated trenches to prevent any accidental melting, carefully log, bag, and pack each section. These precious cores are then shipped in a continuous frozen chain, first to coastal bases by plane or tractor, then onto ships, to specialized laboratories around the world where they are kept in freezers colder than the Antarctic winter itself. This entire logistical ballet is performed to ensure that the ancient air bubbles remain perfectly sealed and uncontaminated from the moment they leave the deep ice until they are analyzed. Once in the lab, the real detective work begins. Researchers use incredibly sensitive instruments to finally unlock the secrets held within the bubbles. One of the most common methods involves placing a section of the core into a vacuum chamber and gently crushing it, releasing the ancient air that has been trapped for millennia. This gas is then funneled into mass spectrometers and gas chromatographs, which can measure the exact concentration of different molecules like carbon dioxide and methane with astonishing precision. The clarity of the data stunned the early pioneers, as one veteran glaciologist recalled upon seeing the first results. It was like turning on a light in a dark room. We had theoretical models of past climate, but here was the raw, atmospheric evidence, showing us the exact composition of the air during an ice age. The data was so clean, so direct, it was almost humbling. These Antarctic cores, particularly the iconic Vostok core, provided the first continuous climate record extending back over 800,000 years. The findings were nothing short of revolutionary. For the first time, scientists could directly observe the intimate dance between greenhouse gas levels and global temperature across multiple ice age cycles. The data revealed a powerful and undeniable correlation. When carbon dioxide and methane levels were low, the planet was colder and locked in a glacial period. When those levels rose, temperatures climbed and the ice retreated. This wasn't just a snapshot, it was a full-length movie of Earth's climate history, providing irrefutable physical proof of the fundamental relationship between atmospheric composition and global climate. This human endeavor, a blend of sheer bravery in the field and meticulous precision in the lab, completely transformed our understanding of how our planet's system works, providing the crucial baseline we use to comprehend the unprecedented changes happening today. But how does something as seemingly simple as ice manage to perform this incredible feat of preservation, locking away samples of our atmosphere for hundreds of thousands of years without any contamination? The process is a fascinating interplay of physics and chemistry, beginning not with solid ice, but with a substance that looks more like coarse sugar. After snow falls, it doesn't immediately turn to ice. Instead, it enters a transitional phase known as firn. This is essentially old snow that has survived a full season of melt, becoming a granular, porous material that can be dozens of meters thick. The air within the firn is still connected to the atmosphere above. It can move freely through the open pores between the granules. It's like a vast, icy sponge sitting on the surface, still breathing with the modern world. The magic happens as more and more snow accumulates on top, applying immense steady pressure to the layers below. This weight slowly compresses the firn, causing the individual granules to sinter, that is, to bond together and gradually deform. Over decades and centuries, the open pores between these granules begin to close off, one by one, isolating pockets of air from the atmosphere above. This critical moment, when the air becomes permanently trapped, is known as the pore close-off. It typically occurs at a depth of about 50 to 100 meters below the surface, depending on local conditions like temperature and snowfall rates. The air sealed inside these bubbles is a direct snapshot of the atmosphere from the time that specific layer was at the surface, effectively fossilizing a moment in our planet's climatic history. Not all ice, however, is created equal in its ability to serve as a perfect time capsule. The quality of the atmospheric record depends heavily on two key factors: temperature stability and snow accumulation rate. In places like central Antarctica, where it is perpetually and extremely cold, the ice remains rigid and stable. There's no risk of summer melting that could cause liquid water to percolate through the layers, potentially mixing gases from different eras and blurring the chemical record. This deep, consistent cold acts as a perfect natural freezer, ensuring the bubbles remain isolated and pristine. Conversely, in slightly warmer regions like some parts of Greenland, seasonal surface melting can sometimes occur, which introduces complexity and requires scientists to be extra cautious when interpreting the gas data from those cores. The rate at which snow accumulates also plays a crucial role. A high accumulation rate, meaning a lot of snow falls each year, is a double-edged sword. On one hand, it quickly buries the snow, shortening the time the firn is open to the atmosphere and potentially providing a higher resolution record with more detail from each year. On the other hand, the rapid burial can generate more heat from compression, slightly warming the deeper layers and potentially altering the very delicate bubbles. A slower accumulation rate results in a longer time for the firn to remain open, which allows for more exchange between the trapped air and the atmosphere above. As one glaciologist explained, it's a bit like trying to take a very quick photograph with a fast shutter speed versus a long exposure. Each method captures a scene, but with different levels of detail and potential for blurring. Scientists have become master detectives, using sophisticated models to understand the precise conditions at each drill site, so they can account for these subtle distortions and fine-tune their interpretations of the ancient air. This rigorous attention to the mechanics of preservation is what gives us such tremendous confidence in the reliability of these frozen archives. So how do scientists translate these tiny, trapped bubbles of ancient air into a detailed story of Earth's past climate? It all comes down to two powerful and precise techniques: isotopic analysis and gas chromatography. Think of it as the process of interrogating the ice, asking it to reveal its deepest secrets one molecule at a time. In specialized labs around the world, researchers begin by carefully shaving the outer layer off a section of ice core to remove any potential contamination from modern air. The pristine inner core is then placed into a vacuum chamber. As the ice is gently crushed or melted, the ancient gases are released, a puff of atmosphere from a world that hasn't existed for tens or even hundreds of thousands of years. This liberated air is then channeled into incredibly sensitive instruments for analysis. One of the most important clues comes from the very composition of the water molecules that make up the ice itself, specifically the ratio of different types or isotopes of oxygen atoms. Water molecules are made of oxygen and hydrogen, but not all oxygen atoms are identical. Most are oxygen-16, which is light, but a small fraction are oxygen-18, a heavier isotope. Now, when ocean water evaporates, the lighter oxygen-16 evaporates more easily than the heavier oxygen-18. As this moist air travels toward the poles and cools, the heavier oxygen-18 condenses and falls as rain or snow first. This means that by the time the air mass reaches the polar ice sheets, the snow that falls is enriched with the lighter oxygen-16. Crucially, this process is temperature-dependent. During colder glacial periods, this distillation effect is even stronger, so the ice formed from that snow has a distinctly different ratio of oxygen-16 to oxygen-18 than ice formed during warmer periods. By meticulously measuring this ratio in each layer of the ice core, scientists can construct a highly accurate thermometer that records the temperature at the time the snow fell, giving them a direct readout of past climate shifts. But the story doesn't end with temperature. The released air bubbles themselves are analyzed using gas chromatography to break down the exact chemical cocktail of the ancient atmosphere. This process separates the different gases, allowing for precise measurement of their concentrations. The two most critical gases are carbon dioxide and methane, powerful greenhouse gases that act like a thermostat for the planet. The data from these analyses have yielded some of the most monumental findings in climate science. The iconic graph from the Vostok ice core, which plots temperature and CO2 levels over 400,000 years, reveals an undeniable lockstep relationship. The two lines rise and fall together in a breathtakingly synchronized dance across multiple ice age cycles. It's a visual proof that when CO2 levels are high, global temperatures are high, and when CO2 levels drop, the planet cools into a glacial period. This correlation isn't just a curious observation. It's a fundamental principle that confirms the profound role greenhouse gases play in regulating Earth's climate. This paleoclimate data is far from just a history lesson. It is the essential bedrock for modern climate models. Before we can trust computer simulations to predict our future climate, they must first be able to accurately simulate the past. Scientists run these models using the greenhouse gas concentrations measured from the ice cores to see if they can successfully predict the temperatures we know occurred. This process of validation is crucial when a model fed with the ice core CO2 data from 20,000 years ago accurately outputs the ice age conditions we know existed. It gives us tremendous confidence in its projections for the next century. The ice core record has effectively allowed us to test our models against real-world experiments run by Earth itself, refining their accuracy and turning them into powerful tools for understanding where we are headed. Each tiny bubble, therefore, is more than a relic. It's a data point in the grandest experiment ever recorded, providing the hard evidence that connects our actions today to the climate of tomorrow. Yet for all the revelations these 800,000-year-old cores have provided, they also mark a tantalizing boundary, a line in the ice that scientists are now passionately striving to cross. The quest to find atmospheric fossils older than 1 million years has become one of the holy grails of modern paleoclimatology. The reason this temporal threshold is so significant lies in a fundamental shift in Earth's climatic rhythm that occurred around that time. Data from other, less precise archives like ocean sediment cores suggest that before 1.2 million years ago, the planet's ice age cycles were different. They appear to have shifted from a dominant 41,000-year pulse to a deeper 100,000-year beat. The ice cores we have give us a front-row seat to the most recent chapters of this story, but they don't show us the pivotal moment when the rhythm itself changed. Finding ice that old would allow us to directly analyze the atmospheric conditions during that major transition, to see what the greenhouse gas levels were doing, and finally understand what caused Earth's climate engine to change gears. The challenge, however, is immense. Ice that has been buried for over 1 million years is exceedingly rare and incredibly difficult to access. The relentless, slow-motion flow of glaciers acts like a geological conveyor belt, but it's also a destructive force. As the ice inches toward the edges of the continent, it is stretched, thinned, and folded under immense pressure. This glacial dynamics can disrupt the delicate, pristine layers, scrambling the chronological order or even warming the base of the ice sheet through friction, which can cause the very bottom layers to melt and their priceless bubbles to be lost forever. Locating a site where the ice is both incredibly old and still perfectly preserved requires a combination of sophisticated radar surveys to map the bedrock below and complex modeling to predict the ice's flow history. It's a needle in a haystack search on a continental scale, looking for that one perfect spot where the ice has remained untouched, cold, and continuous for well over 1 million winters. This formidable challenge has spurred ambitious international collaborations. The most prominent of these is the Beyond EPIC project, which aims to drill a new core in Antarctica that will reach ice up to 1.5 million years old. Building on the success of the original European project for ice coring in Antarctica, which retrieved the 800,000-year record, this new endeavor is a monumental undertaking. Teams have spent years surveying a remote area known as Little Dome Sea, a region with extremely low snowfall accumulation. This is key because less annual snow means the layers are compressed into a thinner column, allowing scientists to reach much further back in time without having to drill to impossible depths. The plan is to drill continuously over multiple Antarctic summer seasons, eventually reaching bedrock at a depth of over 2.7 kilometers. The logistical effort is staggering, involving building a new, state-of-the-art drilling camp in one of the most hostile environments on the planet, all in pursuit of ice that fell as snow when early humans were first beginning to spread across Africa. The potential rewards for crossing this million-year threshold are profound. As one lead scientist on the project put it, we are not just looking for older data, we are searching for a missing piece of the climate puzzle. The transition between the 41,000-year world and the 100,000-year world is the biggest unsolved mystery in Pleistocene climate science. The air trapped in that ice holds the answer. The insights locked in those deepest bubbles could revolutionize our understanding of climate sensitivity, how responsive global temperature is to changes in carbon dioxide. By directly comparing the atmospheric composition before and after the climatic shift, we could finally pinpoint the tipping points and feedback mechanisms that govern these grand planetary scale changes. This knowledge isn't just academic, it's critical for refining the climate models we use to forecast our own future, ensuring they are calibrated against the full range of Earth's behavior. The million-year ice isn't just a record of the past, it's a key to understanding the climate's capacity for change, hidden in the deepest, most ancient frozen cliffs. While we often focus on the ancient air trapped within these ice cores, the frozen cliffs have another incredible secret to share. They are also a detailed record of everything that fell from the sky alongside the snow. Beyond the bubbles, the ice has meticulously catalogued a stunning collection of solid particles, from the finest volcanic ash to dust that journeyed from the stars themselves. These tiny, solid inclusions transform the ice cores from purely atmospheric archives into multi-dimensional historical libraries, capturing events that shaped both our planet and the world beyond it. The process of identifying these particles is a meticulous science in itself. When researchers in the lab analyze a freshly extracted core, they aren't just looking at the clear ice. They are searching for subtle, visible layers that tell a different story. A sudden, thin, grayish band in an otherwise pristine core is an immediate red flag, a signal that a major volcanic eruption occurred somewhere on Earth during the year that snow fell. To confirm its origin, scientists use techniques like electron microscopy and X-ray fluorescence to analyze the chemical fingerprint of the tiny glass shards within the ash. Each volcano has a unique geochemical signature based on the composition of the magma it erupted. By matching the chemical makeup of the ash particles in the ice to known volcanoes, researchers can pinpoint exactly which eruption it came from, even if it happened on the other side of the globe. One of the most powerful examples of this involves a catastrophic event that occurred roughly 74,000 years ago, the super-eruption of Mount Toba on the island of Sumatra. This was one of the largest volcanic events of the last 2 million years, ejecting an unimaginable volume of ash and gas high into the atmosphere. That ash didn't just fall locally. It was carried by global wind patterns, eventually settling as a fine, gray layer across vast distances, including on the pristine ice sheets of Antarctica. When scientists drilling in the Greenland and Antarctic ice cores found this distinct Toba ash layer, it provided a brilliant, globally synchronous time marker. This single, datable horizon allowed archaeologists and climate scientists to precisely correlate their records. It helped refine the timeline of a period of significant global cooling that followed the eruption and, crucially, provided a fixed point to study its potential impact on human populations, offering clues about how such a devastating event might have influenced early human migration patterns and created genetic bottlenecks. But the archives don't just hold earthly secrets, they also contain a sprinkling of stardust. Throughout history, our planet has been constantly bombarded by micrometeorites, tiny particles of cosmic dust, often smaller than a grain of sand, that originate from asteroids and comets. These particles rain down on Earth continuously, landing gently on the snowfields of the polar ice caps. As each new snowfall buries them, they are preserved perfectly within the ice, completely untouched by the weathering processes that would erase them anywhere else. Finding them is like searching for a needle in a haystack, but their unique composition, often rich in nickel and iron, makes them stand out under powerful microscopes. The concentration of these cosmic particles can spike in certain layers, potentially corresponding to known meteor showers or even more significant cosmic events in Earth's past, giving us a direct record of our solar system's history that is written not in rock but in ice. This ability to capture and preserve such a diverse array of materials is what truly elevates the ice core record. As one paleoclimatologist eloquently explained, an ice core is not a single instrument, it's an entire observatory. The bubbles give us the atmosphere's composition, the water isotopes give us the temperature, the volcanic ash gives us a precise calendar, and the cosmic dust gives us a connection to the cosmos. It's this combination that allows us to weave together a coherent, multifaceted narrative of the past. A single core can tell us that a particular year was unusually cold, that the atmosphere was rich in CO2, that a specific volcano on the other side of the world had a massive eruption, and that there was an unusual amount of interstellar dust falling to Earth. This convergence of different data streams transforms the ice from a simple climate log into a comprehensive planetary diary, chronicling the intricate and interconnected forces that have shaped life on Earth for hundreds of thousands of years. This treasure trove of data from the ice cliffs doesn't just live in the past, it serves a profoundly urgent purpose in the present, acting as the ultimate testing ground for the complex computer models we use to forecast our planet's future. Think of climate modeling as building a vast, intricate digital twin of Earth's climate system. These models are built on our understanding of physics and chemistry, how oceans absorb heat, how clouds form, how air currents circulate. But to trust their predictions about where we're headed, we first have to prove they can accurately simulate where we've already been. This is where the atmospheric fossils become absolutely indispensable. They provide the hard, empirical evidence against which these digital simulations are rigorously tested and refined, a process known as calibration. The calibration process is a bit like teaching a navigation system. You wouldn't trust a new GPS app that couldn't correctly identify your current location or retrace a route you just drove. Similarly, climatologists feed their models the known conditions from the past, most critically the precise greenhouse gas concentrations directly measured from the ice core bubbles. They then run the model to see if it outputs the climate we know actually occurred from the other ice core data, like the temperature derived from oxygen isotopes. If the model, when given the CO2 levels from the last ice age, successfully simulates a cold, icy planet, our confidence in it grows. If it doesn't, the discrepancies help scientists identify weaknesses in the model's code. Perhaps the sensitivity of ice sheets to temperature changes was underestimated, or the role of ocean currents was not quite right. This iterative process of testing against the paleoclimate record is what transforms a theoretical exercise into a powerful, evidence-based predictive tool. There are several landmark examples where ice core findings fundamentally reshaped our assumptions and, by extension, our models. For decades, many scientists believed that major climate shifts, like the transition out of an ice age, were slow, gradual processes that unfolded over many thousands of years. The ice cores shattered that notion. Data from Greenland, in particular, revealed evidence of Dansgaard-Easter events, rapid warming spikes where temperatures in the North Atlantic region shot up by a staggering 10 to 15 degrees Celsius in just a few decades, possibly even faster. This was a revolutionary discovery. It proved that Earth's climate system is capable of dramatic, abrupt change, not just the slow, ponderous shifts we once imagined. This finding forced a complete overhaul of climate models to incorporate these non-linear tipping points, the moments where a small push can lead to a massive and potentially irreversible change. It's a chilling reminder that our stable climate is not a given, and it directly informs today's concerns about the stability of systems like the Greenland ice sheet or Atlantic Ocean circulation. Another crucial correction came from understanding the precise relationship between CO2 and temperature. While the lockstep correlation in the Vostok core was clear, the ice cores also revealed a subtle but critical detail. The warming temperatures actually led the rise in CO2 levels by several hundred years during the deglaciation periods. Climate change deniers initially seized on this detail, claiming it proved CO2 doesn't cause warming, but the models informed by this very data revealed the true, more complex story. The initial trigger for warming out of an ice age is actually small changes in Earth's orbit, which cause a slight increase in solar energy. This minor warming then affects the oceans, which are vast reservoirs of dissolved CO2. As the oceans warm, they release this stored CO2 into the atmosphere, which then acts as a powerful amplifier, cranking up the greenhouse effect and driving the majority of the warming. So while CO2 wasn't the initial trigger, it was the overwhelming amplifier that explained the full magnitude of the temperature change. This nuanced understanding, directly gleaned from the ice, is now a cornerstone of every modern climate model, illustrating the critical feedback loops that can accelerate change. This is why climatologists view these frozen archives with such reverence. As one leading modeler stated, "Without the ice core record, our climate projections would be little more than educated guesses." It is the only dataset that provides a long-term, quantitative benchmark for how the entire Earth system responds to greenhouse gases. It tells us not just that CO2 and temperature are linked, but exactly how strong that link has been over 800,000 years. This historical perspective provides the context for our current human-made experiment. When our models, validated by the past, show that the current rapid spike in CO2 is unprecedented in the entire ice core record, the forecast they produce carries immense weight. The data from the cliffs doesn't just tell a story about ancient winters. It provides the crucial, calibrated scale we need to understand the gravity of our modern summer and the storms that may be gathering on the horizon. Yet for all their resilience across millennia, these frozen libraries are facing a threat they have never encountered before: a rapidly warming planet caused by human activity. The very stability that made the polar regions the perfect guardians of our atmospheric history is now being fundamentally undermined. Scientists are witnessing with growing alarm the accelerated melt and destabilization of ice sheets in both Greenland and Antarctica, changes that are happening far faster than many models predicted. We are not just talking about a gradual loss. We are observing a fundamental transformation of these landscapes, putting the entire archive at risk of being lost forever before we even have a chance to read its oldest chapters. The signs of this deterioration are both visible from space and palpable on the ground. In Greenland, the immense ice sheet is not only thinning from the top down due to increased surface melting, but also suffering from accelerated calving, the process where massive chunks of ice break off from the edges of glaciers and tumble into the sea. These calving events are becoming more frequent and more massive, with icebergs the size of cities sometimes shearing away. But the threat isn't just at the edges. Warmer ocean waters are now circulating underneath the floating tongues of glaciers, eating away at them from below and destabilizing them in a way that accelerates the entire flow of ice toward the ocean. This isn't a slow geological process anymore, it's a rapid unraveling. In Antarctica, similar stories unfold. Ice shelves, which act like doorstops holding back the colossal continental ice behind them, are weakening and in some cases catastrophically disintegrating. The loss of these buttresses allows inland ice to flow faster into the sea, further contributing to global sea level rise and, crucially, exposing deeper, older ice to elements it hasn't faced in millions of years. This creates a desperate race against time for the scientific community. Every potential drill site that is lost to the ocean, or every layer of ice that is warmed to the point of melting, represents a unique chapter of Earth's history that is erased permanently. The oldest ice, which is often found near the bedrock and is most vulnerable to geothermal heat and pressure-induced melting, is particularly at risk. As one glaciologist stationed in West Antarctica put it, "It feels like we are historians watching the only copy of a priceless manuscript slowly catch fire." We are scrambling to turn the pages as fast as we can, trying to photograph and preserve every word before it turns to ash and is gone forever. This isn't just about losing data for future research, it's about actively losing our planet's memory. The bubbles of air that have been perfectly preserved for 800,000 years begin to diffuse and mix if the ice warms even slightly. The exquisite chemical details, the precise ratios of gases, the delicate layers of volcanic ash, all of it becomes blurred and eventually lost, turning a crisp, high-resolution record into a muddled, useless smudge. The imagery is both powerful and heartbreaking. Picture one of those ancient ice cliffs, a silent sentinel that has stood watch over a million winters, now beginning to weep streams of meltwater down its face. The very substance that for eons has been the ultimate preserver is now becoming its own destroyer. This meltwater can fracture the ice from within, and when it flows down to the bedrock, it can lubricate the base, causing the entire ice sheet to slide more quickly toward its doom. The fragility of these archives in the face of a warming world underscores the profound stakes. We are not only altering our future climate, we are also irrevocably erasing the past that we need to understand it. The urgent effort to extract and preserve these cores is no longer just a scientific curiosity. It is a rescue mission of global importance, a last-ditch effort to save the stories of a million winters before they melt away into the rising sea, taking their secrets with them. Faced with the dual challenges of reaching ever deeper, older ice and the urgent need to preserve these fragile archives, scientists and engineers have entered a new golden age of innovation, developing remarkable technologies that are revolutionizing every step of the process. The traditional rotary drill, while effective, has limitations. It requires large amounts of drilling fluid to keep the borehole open, and can potentially contaminate the very core it's trying to retrieve, especially when approaching the warm, high-pressure ice near the bedrock. The answer to this problem is emerging not from bigger machinery, but from a beam of concentrated light. Laser-based drilling is one of the most exciting frontiers in ice coring technology. Imagine a device that uses a high-powered pulsed laser to literally vaporize a tiny ring of ice around the core, rather than mechanically grinding through it. This method is incredibly precise, generating far less heat and mechanical stress, which means a drastically reduced risk of fracturing the delicate ancient ice or melting the volatile air bubbles locked inside. Because it requires no drilling fluid, the risk of contaminating the core with modern hydrocarbons is virtually eliminated. While still largely in the prototyping stage, this technology promises to unlock the deepest, most fragile layers of ice with a finesse that mechanical drills could never achieve. But what if we could explore these frozen cliffs without even drilling a massive hole? That's the promise of robotic probes, often called cryobots. These are not the rovers we send to Mars. These are specialized, slimline, thermally powered vehicles designed to melt their way down through the ice sheet, leaving a tiny, refreezing hole behind them. A cryobot is essentially a hot water drill on a wire, but with a sophisticated scientific payload onboard. As it descends, it can use ground-penetrating radar to map the internal layers of the ice around it and sensors to analyze the ice properties in real time. The most ambitious vision is for these probes to eventually reach subglacial lakes, like Lake Vostok, buried under 4 kilometers of Antarctic ice, without ever exposing those pristine, isolated ecosystems to the surface. For ice core science, these robots could be deployed as advanced scouts, traveling ahead of a main drill to identify the most promising, undisturbed layers for extraction, saving immense time and resources. They represent a shift from brute force extraction towards intelligent, minimally invasive exploration. Once a core is retrieved, the next challenge is to analyze it without destroying it. Traditional methods often involved cutting or melting sections of the core, a process that, while effective, is destructive and can only be done once. Non-destructive imaging techniques are changing this entirely. Medical technology has come to the rescue in the form of ultra-high-resolution micro-CT scanners. These devices can create a detailed three-dimensional X-ray map of an entire meter-long core segment without even removing its protective sleeve. Scientists can then digitally, virtually core through this 3D model, examining the precise size, distribution, and even the shape of the trapped air bubbles. They can identify layers of volcanic ash, dust bands, and other inclusions with incredible clarity, all before making a single physical cut. This allows researchers to plan their actual sampling with surgical precision, ensuring they use the minimal amount of precious material for each specific test. It's like having a detailed digital blueprint of a historical document before you ever turn the fragile, ancient page. These technological leaps are not theoretical. They are being put to the test right now in ambitious projects like the Beyond EPIC mission. This international endeavor, building on the success of its predecessor, is a perfect example of how these innovations converge. The team is drilling at Little Dome C, a site chosen after years of radar surveys and modeling identified it as having the perfect combination of low accumulation and stable conditions to preserve 1.5-year-old ice. The drill itself is a masterpiece of engineering, capable of retrieving cores from depths exceeding 2.7 kilometers while maintaining impeccable sample quality. But the mission's success also hinges on the less glamorous, yet equally vital, innovations in logistics, the ultra-clean handling protocols, the custom-built frozen transport chain, and the network of labs around the world standing by to analyze the cores with instruments sensitive enough to detect a few molecules of a gas from a world long vanished. As one lead engineer on the project noted, "We are no longer just drillers, we are time capsule surgeons. The goal is to deliver these samples to the labs in a state that is as close as possible to when they were trapped over 1 million years ago." Every technological advance, from the drill bit to the scanner, is in service of that single goal of preserving fidelity. This relentless drive for innovation is what expands the frontier. It allows us to ask questions we never could before, to reach further back in time with greater confidence, and to read the stories locked in the ice with a clarity that was once the stuff of dreams. The frozen cliffs may hold the secrets, but it is human ingenuity that is finally giving them a voice. Beyond the frozen air and the layers of volcanic ash, the ice holds yet another astonishing secret, a hidden world of ancient life, perfectly preserved in a state of suspended animation. These frozen cliffs have become an unexpected, deeply frozen ark, safeguarding not just the atmosphere of the past, but the very biology that inhabited it. As scientists began to analyze the ice cores with ever more sensitive tools, they discovered that the snow that fell for millennia didn't just trap air, it also captured a microscopic menagerie. Pollen grains from long-vanished forests, spores from ancient fungi, and even entire, intact microorganisms were frozen in time alongside the gas bubbles. This biological treasure trove adds a rich, vibrant layer to the paleoclimate story, transforming the ice cores from a purely physical and chemical record into an ecological one, allowing us to see not just how the climate changed, but how entire ecosystems responded and adapted to those dramatic shifts. The discovery of viable, living microbes in ice that is hundreds of thousands of years old is perhaps the most mind-bending revelation to emerge from this field. Scientists have successfully revived bacteria, fungi, and even viruses from ice core samples after they have been carefully thawed in sterile laboratory conditions. These are not fossils in the traditional sense. They are living organisms that have been in a state of extreme dormancy, essentially pressing the pause button on their metabolism for millennia. The insights gained from studying these ancient survivors are profound. They reveal incredible strategies for resilience, showing how life can persist through the most extreme environmental challenges. Some of these microbes possess unique enzymes and cellular repair mechanisms that allow them to withstand deep freezing, intense radiation, and immense pressure, traits that not only inform our search for life on other icy worlds like Mars or Europa, but also push the boundaries of our understanding of the very limits of life on Earth. This biological archive provides a crucial, complementary dataset to the atmospheric and temperature records. While the gas bubbles tell us the what of climate change, the CO2 levels, the methane concentrations, the biological material tells us the so what. By analyzing the types and abundance of pollen grains preserved in different layers, palynologists can reconstruct the plant communities that existed at the time the snow fell. A sudden shift in the pollen record, from tree pollen to grass pollen, for instance, can pinpoint the exact moment a forest gave way to a tundra as an ice age intensified. It's a direct window into how ecosystems were reshaped by climatic forces. Finding the DNA of ancient mammals, extracted from the soil dust trapped in the ice, offers even more tantalizing clues, potentially allowing scientists to track the migration and population dynamics of species like woolly mammoths or ancient bison in response to the changing world around them. However, this incredible power to resurrect ancient life comes with a weighty ethical responsibility that the scientific community is only beginning to grapple with. The most immediate concern is one of safety. When we revive a microbe that hasn't been seen on Earth for 50,000 years, we have no prior immunity to it. While the vast majority of these organisms are likely harmless, the potential, however small, for an ancient pathogen to cause disease is a risk that requires the strictest possible containment protocols. Beyond the biosafety concerns, there are deeper philosophical questions about our role as time travelers. Does reviving a life form from a different geological epoch constitute a form of ecological time travel with unpredictable consequences? What are the implications of potentially reintroducing genetic material that has been absent from the biosphere for hundreds of thousands of years? These are not just scientific questions. They are ethical dilemmas that require careful consideration from a diverse group of experts, including ethicists, ecologists, and policymakers. The study of this deep frozen biology fundamentally changes our perception of the ice cores. They are no longer seen as sterile, inorganic archives, but as complex, frozen ecosystems in their own right. A single core contains a layered history of life, from the atmospheric conditions above to the microbial communities within. This interdisciplinary approach, merging climatology with microbiology and ecology, gives us the most holistic view of our planet's history ever assembled. It shows us that climate change is never just about numbers on a graph. It is a powerful force that rewrites the story of life itself, determining which species thrive, which adapt, and which vanish into the deep freeze of history. As we continue to probe these frozen cliffs, we are not just reading a climate history. We are leafing through the pages of a biological epic, written in DNA and pollen, waiting patiently in the ice for its story to be told. Perhaps one of the most compelling aspects of these atmospheric fossils is their ability to act as a universal calendar, allowing us to sync the timelines of Earth's natural history with the rise and fall of human civilizations. The tiny particles and chemical signatures trapped within the ice create a series of global bookmarks, moments in time that are recorded identically in the frozen layers of both Greenland and Antarctica. When a massive volcano erupts, it injects a unique cocktail of sulfates and ash high into the atmosphere, where it can circle the globe for years. These particles eventually fall to the surface, landing on ice sheets and becoming sealed within the annual snow layers. By identifying these identical volcanic horizons in ice cores drilled from opposite ends of the planet, scientists can perfectly align their timelines, creating a synchronized year-by-year chronicle of the past. This precise dating turns the ice into a master key, allowing historians and archaeologists to take events from human history, a famine, a migration, the collapse of a dynasty, and cross-reference them with an exact climatic condition from that very same year, half a world away. This powerful dialogue between ice and parchment is perfectly illustrated by the turmoil of the Little Ice Age, a period of pronounced cooling that gripped much of the world from around the 14th to the 19th centuries. While historical diaries and paintings from Europe vividly describe rivers like the Thames freezing solid and glaciers in the Alps advancing to swallow entire farms, the ice cores provide the hard, quantitative data to understand the global scale and persistence of this cold period. Cores from Greenland and the Andes show a clear, prolonged dip in temperatures, while layers of volcanic sulfates point to a series of massive eruptions that likely kicked off the cooling by spewing sunlight-blocking particles into the stratosphere. This climatic shift wasn't just an inconvenience, it was a civilization-altering event. Crop failures became widespread, leading to catastrophic famines across Europe. The price of grain skyrocketed, social order frayed, and mass migrations began as people searched for food and warmth. The ice core record shows us that this wasn't a localized European phenomenon. It was a global climate event that stretched from the mountains of South America to the high Arctic, providing the environmental context for a period of profound human suffering and adaptation. We can push this scientific corroboration even further back in time to the very cradle of civilization itself. The mighty Akkadian Empire in Mesopotamia, often considered the world's first true empire, collapsed with stunning rapidity around 4,200 years ago. For centuries, historians attributed its fall to social unrest or invasion. But then, ice cores from glaciers in the Andes and sediment cores from the Gulf of Oman revealed a startling new clue, a dramatic, multi-decade megadrought that gripped the region at the exact same time. The evidence was in the dust. Layers within the ice cores showed a massive spike in wind-blown dust particles, indicating that arid conditions had stripped the land of its protective vegetation. The empire's agricultural heartland, entirely dependent on irrigation, would have simply desiccated. The Akkadian collapse now appears not as a simple political failure, but as a devastating climate-induced societal breakdown, a story told not just in ruined ziggurates, but in the microscopic dust grains trapped in ancient ice. This fusion of ice core data with the human story fundamentally enriches our understanding of history. It moves us beyond simplistic narratives of great leaders and battles, and toward a more nuanced view that acknowledges the powerful role of environmental forces. A historian specializing in ancient Rome might study tax records showing a sudden drop in grain shipments from North Africa, while an ice core scientist examining a core from the Alps finds chemical evidence of a prolonged drought there at the exact same time. Suddenly, a political decision made by an emperor in Rome can be seen as a desperate response to a climate shock he could never have understood. The ice doesn't just give us data, it provides the missing context, the backdrop against which human ambition, resilience, and fragility played out. It shows us that our history has never been separate from the environment. We have always been active participants in a deeply interconnected planetary system, responding to its shifts and, as we now know, beginning to influence them ourselves. This incredible power to reach into the deep past and extract its secrets comes with a profound and complex set of ethical responsibilities that the scientific community is now actively grappling with. On the surface, extracting a cylinder of ice might seem like a minor intrusion in a vast, empty wilderness, but these polar landscapes are not truly empty. They are the last truly pristine environments on Earth, and any human activity, no matter how carefully planned, leaves a footprint. The very act of establishing a deep field drilling camp requires transporting tons of equipment by plane and tractor, burning fossil fuels in an environment exceptionally vulnerable to pollution. The drilling process itself involves using hundreds of gallons of drilling fluid, typically a petroleum-based product like kerosene, to keep the borehole from collapsing under pressure. A single spill, however contained, could introduce contaminants into the ancient, pure ice and snow, a stain that would persist for centuries. The protocols to prevent this are extraordinarily strict, involving double-walled containment vessels and meticulous handling procedures, but the risk, however small, forces a difficult question. Is the knowledge we gain worth the potential, irreversible damage to these sacred, frozen places? This leads to a deeper philosophical debate about the nature of these resources and who they truly belong to. The ice cores themselves are a non-renewable archive. Once a specific layer is drilled, analyzed, and used up, it is gone forever. There is no going back for a second sample. This has sparked a serious conversation within international glaciology circles about the concept of heritage ice, sections of the ice sheet that should be designated as protected, left completely untouched for future generations who will undoubtedly have even more advanced and less invasive technologies at their disposal. The argument is that we have a responsibility to be more than just consumers of this planetary memory. We must act as its stewards, preserving some of its deepest chapters so that scientists 100 or 500 years from now can answer questions we haven't even thought to ask yet, using methods we cannot yet imagine. It is a humbling exercise in intergenerational ethics, acknowledging the limits of our current right to know. Furthermore, the question of ownership and access to these priceless cores is critical to ensuring this science remains equitable and globally beneficial. The ice is extracted from territories that are governed by international treaties, like the Antarctic Treaty System, which designates the continent as a natural reserve devoted to peace and science. However, the actual drilling projects are enormously expensive, typically funded and led by a consortium of wealthy nations. This creates a potential power imbalance where the countries that can afford to go and get the ice also control access to the samples and, by extension, the data and the resulting scientific narrative. To counter this, organizations like the International Partnerships in Ice Core Sciences have established strict protocols for sample curation and data sharing. Ice cores are meticulously archived in national repositories, like the National Science Foundation's Ice Core facility in Colorado, which operates like a library of ice. Scientists from anywhere in the world can submit a research proposal to receive a piece of a core for their own analysis, ensuring that a researcher from a developing nation has the same opportunity to study these global treasures as one from the country that funded the drill. This system aims to democratize the past, treating the ice as a common heritage of humankind. Perhaps the most vital and often overlooked perspective in this ethical landscape is that of indigenous communities, particularly in the Arctic regions of Greenland and northern Canada. For these communities, the ice is not an inert resource or a mere data repository. It is a living, integral part of their culture, their history, and their homeland. It is the ground they walk on, the sea they travel, and a fundamental element of their worldview. While many communities are strong supporters of science that helps understand climate change, a process that disproportionately affects them, they also rightly demand a seat at the table when projects are planned on their ancestral lands. This involves moving beyond simple consultation to genuine collaboration, incorporating indigenous knowledge about the land, its conditions, and its history into the scientific process itself. An environmental ethicist working with Arctic communities framed it this way: "We are used to asking, can we drill here, from a technical and logistical standpoint. But we must learn to also ask, should we drill here? And that question cannot be answered by scientists and engineers alone. It requires listening to the people for whom this ice is home, and respecting that their connection to the land carries a wisdom that our data points cannot capture." This evolving dialogue is transforming polar research from a purely extractive endeavor into a more respectful and holistic partnership, ensuring that the quest to understand the planet's past is conducted in a way that honors all of its present guardians. Despite the overwhelming scientific consensus on their reliability, the world of atmospheric fossils is often clouded by public misconceptions, some of which can obscure the incredible truth these icy archives hold. One of the most common mix-ups is right in the name itself. The term fossil often conjures images of dinosaur bones or imprints of leaves in stone, leading some to imagine that scientists are chiseling ancient air bubbles out of solid rock. In reality, these are not literal fossils in that traditional sense. They are pristine, physical samples of the actual ancient atmosphere, perfectly preserved in a frozen state. It's the difference between finding a photograph of a historical event versus finding a written description of it. One provides direct, tangible evidence, while the other is an interpretation. These bubbles are the photograph, offering a direct look at the air itself, unchanged for hundreds of thousands of years. Another persistent myth suggests that the data extracted from these ice cores is largely speculative or based on best guess estimates. This misconception often stems from a lack of awareness about the incredibly rigorous and multi-layered dating methods scientists employ. Dating the ice isn't done with a single technique. It's a process of cross-verification that would impress any detective. Scientists first establish a preliminary timeline by simply counting the annual layers, much like counting tree rings. Each year's snowfall creates a distinguishable band of summer and winter snow. But to ensure absolute accuracy, they then cross-reference this count with known, independently dated events. For instance, a specific layer of volcanic ash with a chemical signature matching a massive eruption that historians have dated to the year exactly 74,000 years ago provides a brilliant fixed anchor point in the core. If the layer count matches that known date, confidence soars. Furthermore, they can use records of solar cycles or even the radioactive decay of elements trapped in the ice to confirm the timeline. This isn't a single guess. It's a web of evidence where different methods from different fields all point to the same conclusion, creating a timeline that is as robust and verified as any in science. Perhaps the most technically argued criticism is the idea that the ice core record has been compromised over millennia by processes like melting or diffusion, which would mix the ancient air and make it useless. It's a reasonable concern on its face. After all, how could something remain perfectly sealed for so long? The answer lies in the unique, profoundly stable environment of the polar ice sheets. In central Antarctica, the temperature has remained consistently far below freezing for hundreds of thousands of years. There is simply no liquid water present to cause melting that would mix the layers. As for diffusion, the slow movement of gases through the ice, scientists are not only aware of this possibility, they can measure it and account for it with exquisite precision. The extremely dense, crystalline structure of deep ice acts as a powerful barrier, slowing diffusion to an absolute crawl. By studying the physical properties of the ice at different depths and temperatures, glaciologists have developed sophisticated models that can correct for any tiny amount of gas movement that might have occurred, ensuring the final data reflects the original atmosphere with remarkable fidelity. It's like having a slightly blurry photograph. Advanced software can sharpen the image to reveal the clear details underneath. To make this all a bit more relatable, consider a simple analogy. Think of the ice sheet as a multi-layered birthday cake that has been baked and frozen solid for a century. Each layer of frosting represents a year of snowfall. Trapped within each layer are a few sprinkles. Those are our air bubbles. Now, if you left a regular cake out on the counter, the frosting layers might melt and run together, blurring the sprinkles from different years. But because this cake has been in a deep freeze the entire time, every layer remains perfectly distinct, and the sprinkles are locked in their original place. Scientists are the master bakers who can carefully slice through this frozen cake, isolate the sprinkles from a specific layer, and tell you exactly what flavor they are, representing the air from that exact year. This process of careful extraction and analysis, backed by cross-checking with other historical records, is what transforms these frozen cliffs from passive ice formations into the most trusted chroniclers of our planet's atmospheric history. By directly confronting these myths with clear, accessible explanations, we can fully appreciate the meticulous work that makes these archives the gold standard for understanding Earth's climate story. While the Antarctic cores provided the grand, sweeping narrative of Earth's climate over 800,000 years, it was a monumental effort in the Northern Hemisphere that delivered a story of breathtaking speed and drama, fundamentally changing our perception of how quickly climate can shift. The Greenland Ice Sheet Project, known as GISP, became a legend in the field, not for the sheer age of its ice, but for the stunningly high-resolution detail it captured, revealing that our planet's climate is capable of changing not over millennia, but within a single human lifetime. This ambitious endeavor primarily focused on drilling at a site called Summit Station at the very top of the Greenland ice sheet, was a massive international collaboration, bringing together scientists and funding from the United States and several European nations. Their shared goal was to pull up a continuous record of the last glacial period, but what they found was far more turbulent and electrifying than anyone had anticipated. The high resolution of the Greenland cores was a direct result of the local climate. Unlike the dry, low snowfall interior of Antarctica, Greenland receives a comparatively generous amount of snow each year. This meant that the annual layers of accumulation were much thicker, making them dramatically easier to distinguish from one another. Where an Antarctic core might compress a century into a few centimeters of ice, a Greenland core could stretch that same century out over a much longer segment, preserving an incredible amount of detail. Scientists could literally see the individual years like pages in a book, allowing them to pinpoint events with astonishing precision. This clarity turned the Greenland ice core into a slow-motion camera on the past, capturing changes that were simply too fast and too fine to be detected in the longer, but more compressed Antarctic record. It was this incredible resolution that revealed one of the most shocking discoveries in modern climate science, the Dansgaard-Easter events. Named after the Danish paleoclimatologist Willy Dansgaard and the Swiss climatologist Hans Easter, these events were dramatic temperature roller coasters that occurred during the last ice age. The data showed that Greenland's temperature would sometimes skyrocket, warming by a staggering 10 to 15 degrees Celsius in as little as a few decades, perhaps even faster. The ice would then hold this new, much warmer state for centuries before abruptly plunging back into glacial cold. Imagine the climate of Oslo, Sweden, shifting to something more akin to Madrid, Spain, in the span of a single generation, and then just as suddenly reversing course. These were not minor fluctuations. They were violent, planetary-scale convulsions that would have completely upended ecosystems and any human societies that existed at the time. The evidence for these rapid shifts is locked in the oxygen isotope ratios within the ice itself. As we've discussed, a higher ratio of the lighter oxygen-16 isotope indicates warmer conditions. In the Greenland cores, the lines graphing this ratio don't show gentle slopes. They show near vertical spikes, shooting upward and then crashing back down. To put this into a modern context, the amount of warming that occurred at the onset of these events was about 10 times greater than the total warming the Earth has experienced since the end of the last ice age, and it happened at least 25 times faster. This discovery was a paradigm-shifting moment. It proved conclusively that Earth's climate system possesses powerful and abrupt tipping points, capable of flipping from one stable state to another with breathtaking speed. The notion of a slow, sluggish climate system was forever shattered. The cause of these dramatic jumps is now believed to be linked to sudden changes in the Great Ocean Conveyor Belt, the Atlantic Meridional Overturning Circulation, which moves vast amounts of heat around the planet. The theory suggests that this circulation can sometimes stall and then suddenly restart, acting like a massive switch for Northern Hemisphere climate. The Greenland ice cores provided the crucial, irrefutable evidence that this had happened repeatedly in the past, which immediately raised a critical and urgent question for our future. Could human-induced climate change potentially trigger a similar abrupt shift in our own time? This finding moved the discussion out of purely academic circles and directly into the realm of risk assessment and policy, highlighting a vulnerability in our climate system that was far more immediate and dangerous than previously understood. The legacy of the Greenland Ice Sheet Project, therefore, extends far beyond the pages of scientific journals. It provided the hard, physical evidence for climate instability that became a cornerstone of reports by the Intergovernmental Panel on Climate Change. Policymakers and world leaders began citing this paleoclimate data to argue for more aggressive emission reduction targets, using the abrupt changes of the past as a cautionary tale for what might be possible in our future. The project stands as a powerful testament to what international scientific collaboration can achieve, demonstrating that the most fragile, frozen places on Earth hold the keys to understanding not only our planet's history, but the potential trajectories of our collective future. It transformed our view of climate from a slow-moving giant to a system that can, under the right pressures, change with a stunning and disruptive swiftness. Looking ahead, the field of paleoclimatology is poised for a transformation as dramatic as the initial discovery of those first ice cores, driven by a convergence of bold engineering, computational power, and interdisciplinary thinking. The quest won't stop at 1.5-million-year-old ice. The next horizon is finding ice that's 2 million or even older, pushing further back into Earth's deep-time climate history. This will require venturing beyond the classic dome summits to more challenging, dynamic regions of Antarctica, like the rugged Gambutsev Mountains hidden beneath the ice sheet. Here, the ice is thick and ancient, but its flow is complex, demanding new radar technologies and autonomous drones to map the hidden bedrock topography in exquisite detail before a drill ever touches the surface. The future of drilling itself is likely laser-based and minimally invasive, allowing us to retrieve the most fragile, deepest ice without the risk of contamination from drilling fluids, preserving every precious bubble in its original state. The sheer volume of data emerging from these new cores, combined with existing archives, is becoming so vast that human analysis alone is no longer sufficient. This is where artificial intelligence is stepping in, not to replace scientists, but to act as a powerful partner. Machine learning algorithms are now being trained to scan thousands of meters of ice core imagery, automatically identifying annual layers, pinpointing volcanic ash horizons, and even detecting subtle abnormalities that might indicate a past climatic event a human eye could easily miss. These ice systems can process decades of data in a matter of hours, uncovering complex, non-linear patterns and correlations within the climate system that have remained hidden until now. One researcher described it as finally having the tool needed to read every single word in the planet's diary simultaneously, rather than just skimming a few pages here and there. This computational power will allow us to move from describing what happened in the past to truly predicting how the climate system behaves under extreme duress. This deeper understanding will inevitably fuel one of the most critical and contentious debates of our time, geoengineering, as data from the ice cores reveals just how sensitive the climate is to aerosols in the atmosphere, both from volcanic eruptions and potentially human intervention. It provides a crucial, evidence-based framework for evaluating proposals to deliberately cool the planet. For instance, by studying the precise climatic effects of past mega-eruptions recorded in the ice, scientists can better model the potential outcomes and unintended consequences of spraying reflective particles into the stratosphere to block sunlight. The ice core record acts as a natural laboratory, offering case studies of how the planet reacted to similar forcings in the past. This isn't an endorsement of such strategies, but rather a provision of the essential paleodata needed to have an informed, rational discussion about risks, ethics, and efficacy, moving the debate from science fiction into the realm of evidence-based science. The scope of exploration is also expanding beyond our own planet. Scientists are drawing direct parallels between the techniques developed for drilling into Earth's ice sheets and the proposed missions to search for life on icy moons like Europa and Enceladus. The cryobots being tested in Antarctica today are direct prototypes for the probes that might one day melt through kilometers of alien ice to explore the hidden oceans below. Furthermore, the methods used to detect and analyze ancient, dormant microbes in terrestrial ice cores are informing the design of instruments that could look for signs of life in extraterrestrial ice. A prominent planetary scientist recently noted that the frozen cliffs of Antarctica are the best analog we have for the outer solar system, making paleoclimatologists unexpected but essential contributors to the future of astrobiology. The ultimate goal is to weave all these threads, deeper ice, smarter computers, and planetary science, into a seamless, integrated understanding of Earth as a complete system. Future research will increasingly fuse the high-resolution past from the ice cores with real-time data from satellites monitoring current changes in ice sheet volume, ocean temperature, and atmospheric chemistry. This creates a powerful feedback loop where the past helps us calibrate our observations of the present, and the present helps us better interpret the clues left in the past. This holistic view is what will allow us to build the most robust climate forecasts yet, turning paleoclimatology from a historical science into a foundational pillar for navigating the future. The next generation of scientists won't just be drillers or lab technicians. They'll be system thinkers, armed with the deepest history book on Earth, ready to write a more informed and hopeful chapter for humanity. The profound insights gleaned from these frozen archives are no longer confined to university labs and scientific journals. They are now sparking curiosity and shaping young minds in classrooms around the world. Educators have recognized that ice core science is a perfect gateway to teaching a multitude of subjects, from hard sciences like chemistry and physics to interdisciplinary studies in history and ethics. It provides a tangible, awe-inspiring narrative that turns abstract concepts into a gripping detective story. Instead of just memorizing the fact that carbon dioxide levels are rising, students can examine the actual data points, those precise measurements of ancient air, and see the undeniable, dramatic spike of the last century plotted against 800,000 years of natural variability. This transforms climate change from a political talking point into an evidence-based reality, empowering students with the knowledge and critical thinking skills to understand the world they are inheriting. This learning often begins with incredibly engaging, hands-on activities that demystify the complex process of ice core extraction. In schools from Alaska to Australia, students don't just read about drilling, they get to simulate it themselves. A common project involves creating a model ice core using layers of frozen water mixed with different colored sand or glitter to represent volcanic ash and dust bands from various eras. Using a simple manual drill or even a straw, students carefully extract their own core, then work to identify and count the layers to establish a timeline. This tactile experience makes the science immediately accessible, teaching them about stratigraphy, the study of rock or soil layers, and the painstaking care required to preserve a historical record. It's one thing to hear about annual layers, it's another to carefully reveal them with your own hands, instantly conveying the patience and precision of real-world scientists. The exploration continues as students graduate to analyzing proxy data. Much like the professionals do, teachers provide simplified datasets derived from real ice core research, perhaps graphs showing the correlation between temperature and CO2 over a specific glacial-interglacial cycle. Students are tasked with interpreting these graphs, identifying trends, and drawing conclusions about cause and effect. They might be presented with a layer marked by a high concentration of sulfates and challenged to research which major volcanic eruption in human history it could correspond to, effectively becoming historical sleuth using scientific evidence. These exercises go beyond rote learning. They foster data literacy and analytical reasoning, showing students how we know what we know about the past. It teaches them that scientific knowledge isn't just a collection of facts, but a process of interrogation and validation. Recognizing that not all schools have equal access to resources, several innovative programs are dedicated to bridging this gap and bringing this exciting science directly to underserved communities. Organizations like Polar Educators International and the U.S. Ice Drilling Program often host virtual field trips where SCIENTIST's Chinese letter from remote drilling camps in Greenland or Antarctica, answering questions from students in real time. They also assemble and distribute classroom kits that include everything a teacher needs: miniature ice core samples embedded with bubbles, lesson plans, and analysis activities, allowing a school with limited funding to offer the same rich experience as any other. Furthermore, some university outreach programs specifically target Title I schools, sending graduate students into classrooms to lead workshops and mentor students, demonstrating that a career in science is an achievable path for everyone. This focused effort ensures that the crucial understanding of our climate history and future isn't a privilege for a few, but a fundamental part of education for all. Ultimately, the goal of integrating ice core science into education is to cultivate a sense of environmental stewardship. When a student holds a piece of plastic that contains bubbles of air from the time of the Roman Empire, it creates a powerful, emotional connection to the past and a deep sense of responsibility for the future. They begin to see themselves not as separate from Earth's history, but as active participants in its longest-running story. This knowledge moves them from passive observers to informed citizens, equipped to engage in conversations about climate policy, sustainability, and conservation with a foundation of evidence and context. It shows them that the choices we make today about energy, transportation, and consumption will become the chemical signals in the ice layers of the future, a permanent part of the planetary record. By understanding these frozen cliffs, students learn that they are the first generation to fully comprehend this intricate climate story, and perhaps the last with the opportunity to change its most urgent and dangerous chapter. Beyond the hard data and scientific papers, the profound narrative of ice cores has seeped into our collective cultural consciousness, inspiring artists, filmmakers, and writers to explore their deeper meaning. These atmospheric fossils have become powerful metaphors in the creative world, symbolizing everything from the fragility of memory to the immense weight of deep time and the indelible mark humanity leaves on the planet. Artists are drawn to the sheer poetry of the object itself, a solid, physical cylinder that contains something as intangible and essential as ancient air, a perfect fusion of the concrete and the ephemeral. This intersection of science and art creates a vital dialogue where data is translated into emotion, allowing a much broader audience to connect with these concepts on a visceral level, far beyond what a graph or chart could ever achieve. One of the most direct ways this manifests is through documentary filmmaking, where directors have turned the meticulous process of ice core drilling into a form of high-stakes cinematic drama. Films like Ice and the Sky or segments in major nature series use breathtaking cinematography to capture the stark beauty of the polar landscapes and the intense human endeavor required to retrieve these archives. The whirring of the drill, the slow, careful extraction of a glistening core from the depths, and the focused faces of the scientists in the frigid cold are all framed with a reverence that elevates the scientific process to an almost spiritual quest. These visuals are paired with narratives that emphasize the urgency of the climate crisis, using the ice core's timeline as the central plot device. The audience isn't just told about a million years of history, they are shown the very act of recovering it, making the science feel immediate, tangible, and profoundly heroic. Visual artists and installation creators have taken a more tactile approach, often incorporating actual ice or ice core imagery into their work to create powerful, experiential pieces. Consider an installation where a large block of clear ice, embedded with layers of sediment and objects, slowly melts over the course of the exhibition, dripping into a pan below, a direct and unsettling metaphor for the transient nature of our environmental record and the urgency of preservation. Other artists work with photomicrography, creating stunning, large-scale prints of the ice itself, revealing the beautiful, otherworldly structures of the crystals and the trapped bubbles that are invisible to the naked eye. These pieces transform scientific specimens into objects of awe, inviting viewers to lean in and contemplate the stories contained within each tiny, frozen cell. Some creators have even used data sonification, turning the chemical concentrations from different depths in a core into a musical composition, where a rise in carbon dioxide becomes a dissonant, climbing chord that grows more intense as the piece moves toward the present day, creating an auditory experience of climate change that is both innovative and deeply moving. The allure for these creators often stems from the unique way ice cores compress deep time into a manageable, almost magical form. A novelist might describe holding an ice core as holding 1,000 centuries in your hands, a physical object that makes the abstract concept of geologic time suddenly feel immediate and personal. One sculptor who worked with ice core data for a major exhibit explained that she was captivated by the elegant melancholy of the archives. They are these perfect, beautiful records, she said, but they also tell a story of loss. They show us what we had, what we are changing, and what we stand to lose. As an artist, that tension between beauty and tragedy is incredibly fertile ground. This perspective highlights why these natural archives are so compelling. They are not passive records, they are active witnesses, and artists are drawn to giving that witness a voice. This fusion of disciplines does more than just create beautiful objects. It builds a crucial bridge of understanding. A complex scientific concept like orbital forcing or Dansgaard-Easter events can be difficult for the public to grasp, but an artist's interpretation of that same concept through a sculpture, a dance performance, or a soundscape can communicate the emotional weight and significance instantly. Art can convey the wonder of discovery, the anxiety of uncertainty, and the profound responsibility we have as a species, all without requiring a PhD to understand. It translates the language of data into the language of feeling, engaging viewers on a human level and fostering a deeper, more personal connection to the planet's story. This celebration of the intersection between science and creativity reminds us that understanding our world isn't just a technical pursuit. It's a deeply human one, requiring not just our minds, but our hearts and our imagination to fully comprehend our place within the vast, frozen tapestry of time. While ice cores provide an unparalleled record of the atmosphere, they are just one of the powerful tools in the paleoclimatologist's toolkit. To build the most complete picture of Earth's past, scientists must also turn to the vast archives preserved beneath the world's oceans and lakes. Sediment cores extracted from the bottoms of these watery basins offer a dramatically different but equally vital perspective, and understanding their strengths and weaknesses is key to appreciating the full story. Imagine the ocean floor not as a barren wasteland, but as a slow, steady, and continuous filing system. For millions of years, a gentle rain of microscopic shells, dust particles, pollen, and other debris has settled through the water column, accumulating layer by patient layer on the seabed. This process creates a chronological record that can extend back tens of millions of years, far beyond the reach of even the oldest Antarctic ice. The fundamental difference between these two archives lies in what they preserve best. An ice core is the undisputed champion of atmospheric snapshots, offering a direct, high-fidelity sample of the ancient air itself with incredible temporal resolution. In the best scenarios, like the Greenland cores, scientists can distinguish individual years or even seasons, allowing them to track changes that happened within a human lifetime. A sediment core, by contrast, is a master chronicler of the oceans and the broader Earth system. By analyzing the fossilized shells of tiny creatures called foraminifera found in these sediments, researchers can reconstruct past ocean temperatures and acidity levels. The types of pollen grains preserved tell the story of shifting vegetation and rainfall patterns on land, while layers of coarse-grained sediment can indicate periods of intense iceberg activity. However, this record is almost always a blurrier picture. The constant burrowing of bottom-dwelling organisms, deep ocean currents, and the gradual compression of the mud itself can mix the layers, smoothing out the fine details and making it difficult to pinpoint events with the same razor-sharp annual precision that ice allows. This trade-off between resolution and duration is the central dynamic when comparing these methods. Think of it like two different cameras. An ice core is a high-speed camera with an incredibly fast shutter speed, capturing a crisp, clear, and detailed image of a specific moment in time. A sediment core is a time-lapse camera set to a very slow interval. It captures an immensely long stretch of time, but each frame represents a century or even a millennium, blending countless individual events into a broader trend. This is why the two are not competitors, but essential collaborators. The long, sweeping narrative from ocean sediments provides the grand context, the overarching plot of Earth's climate story across millions of years. The ice core then zooms in on the most recent chapters of that story, providing the intricate dialogue and the fast-paced action that gives the broader plot its meaning and urgency. A perfect example of this powerful collaboration is how these archives helped resolve a major scientific debate about the rhythm of the ice ages. For a long time, data from marine sediments, which showed a dominant 100,000-year cycle of glaciations, seemed to conflict with the astronomical theory of Milankovitch cycles, which suggested that changes in Earth's orbit and tilt should cause a stronger 41,000-year cycle. The much longer sediment record clearly showed the 100,000-year pattern, but couldn't explain why it was so dominant. It was the high-resolution ice cores that helped crack the case. By providing exquisitely detailed records of greenhouse gas concentrations and temperature, the ice cores revealed that while the initial trigger for the ice age cycles was indeed the 41,000-year orbital cycle, the changes in CO2 and methane acted as a powerful amplifier, stretching and intensifying the response into the longer, 100,000-year rhythm we see so clearly. The sediment record. The sediments showed what the pattern was, but it took the ice cores to reveal how it worked. This integrative approach, using multiple proxies from different archives, is the gold standard in paleoclimatology. It's a form of scientific cross-examination, where the evidence from one source is used to test and validate the findings from another. When the temperature signal from an ocean sediment core aligns with the atmospheric CO2 levels from an ice core for the same time period, the confidence in both records skyrockets. It creates a robust, multi-dimensional understanding of the past, where the chemistry of the air, the temperature of the sea, and the biology on land are all woven together into a single, coherent narrative. This holistic view is crucial because Earth's climate system is an incredibly complex machine. You cannot understand the whole by studying just one of its parts. The frozen cliffs give us the atmosphere's vital signs, while the deep sea mud tells the story of the oceanic circulation that moves heat around the globe. Only by listening to both of these ancient witnesses can we truly begin to comprehend the magnificent and intricate symphony of our planet's history. This hard evidence from the ice cores moved the conversation from theoretical models to irrefutable fact, providing the scientific backbone for the most significant global climate agreements of our time. The Intergovernmental Panel on Climate Change, or IPCC, relies heavily on this paleo data to establish baseline conditions for the planet and to define what truly constitutes unprecedented change. Their landmark reports, which synthesize thousands of studies for world leaders, consistently feature the iconic graphs from Vostok and other ice cores, visually demonstrating how current atmospheric carbon dioxide levels, now exceeding 420 parts per million, have rocketed far beyond the natural ceiling of 280 to 300 parts per million that steady for the entire 800,000-year record. This isn't a gradual uptick, It's a vertical spike completely outside of natural variability, and it's the ice cores that make this undeniable. This long-term perspective provided by the atmospheric fossils is what allows scientists to set specific, quantifiable benchmarks for a safe climate, translating abstract concerns into concrete targets for global action. The most prominent example of this direct influence is the Paris Agreement of 2015. The very goal of limiting global warming to well below 2 degrees Celsius above pre-industrial levels and pursuing efforts to limit it to 1.5 degrees is fundamentally rooted in the ice core record. This temperature target isn't arbitrary. It's derived from climate models that are themselves calibrated and validated against the paleoclimate data. Scientists can look at the ice cores and see that when CO2 levels were at a certain concentration in the past, global temperatures were a certain number of degrees higher or lower. This historical relationship between cause and effect provides the crucial math that connects our emissions today to the warming we can expect tomorrow. Furthermore, the agreement's emphasis on achieving net zero emissions in the second half of this century is a direct response to the ice core evidence showing that temperature and CO2 are in lockstep. To stabilize the climate, we must first stabilize and then dramatically lower the concentration of greenhouse gases in the atmosphere. Policymakers and diplomats have wielded this evidence in high-stakes negotiations to cut through political obstruction and build a case for urgent, ambitious action. Former U.S. Secretary of State John Kerry, during the lead-up to the Paris talks, frequently invoked the paleoclimate record, stating, "The ice cores don't lie. They show us a planet that has never experienced this kind of change this fast. We are conducting a reckless experiment with the only home we have." This powerful use of the data shifts the argument from a debate about opinions to a confrontation with objective, physical reality. It was instrumental in convincing many nations to agree to more aggressive emission reduction pledges, known as nationally determined contributions, by providing a shared, undeniable scientific foundation for the talks. The cause created a common reference point that transcended geopolitical disputes, uniting the world around a set of facts preserved in ice for all of humanity to see. The practical importance of these natural records extends beyond setting targets to shaping the very mechanisms of the agreements. The concept of a global carbon budget, the finite amount of CO2 we can still emit before blowing past the 1.5 or 2 degree limits, is calculated using complex models that are steeped in paleo data. The ice cores tell us how the climate system responded to past changes in CO2, which allows scientists to estimate its sensitivity to our current pollution. This budget framework has become a central tool for holding countries accountable, providing a clear numerical measure of progress or lack thereof. Without the million-year context provided by the frozen cliffs, we would be navigating the climate crisis with a dangerously incomplete map. These atmospheric fossils have done more than just inform policy. They have provided the moral and scientific imperative for it, offering a silent testimony from Earth's past that is now shouting a warning about our future. Behind every meter of ice core and every data point revealing Earth's secrets, there are people, scientists and engineers who trade comfort for discovery, living for months at a time in some of the most extreme environments on the planet. The reality of life at a remote drilling camp is a world away from a sterile laboratory. Imagine waking up in a cramped, unheated tent, the air inside so cold that your breath forms a permanent frost on the fabric above your head. The first chore of the day isn't checking emails, it's just staying warm. Dressing is a meticulous, layered ritual, a battle against a cold so profound that exposed skin can freeze in under a minute. The simple act of drinking water requires constant vigilance, as a neglected bottle will turn to solid ice within the hour. This is the daily rhythm of a field season in Antarctica or on the Greenland ice sheet, a test of endurance where the environment is a constant, demanding presence. Yet within this austerity, a powerful and unique sense of community flourishes. Isolated together, cut off from the rest of the world, the crew at a drilling camp becomes a close-knit family. There are no hierarchies here. The lead glaciologist shares dishwashing duties with the graduate student, and the drill engineer plays cards with the camp manager. Meals become the central social event, a time to share stories, debate findings, and offer support. A researcher from India might describe the monsoons of her homeland to a glaciologist from Norway, while a technician from Chile shares photos of his family. This forced proximity and shared struggle break down barriers, creating an environment of incredible collaboration and mutual respect. The isolation fosters a deep camaraderie, a collective spirit where everyone is united by a single, monumental goal: to bring back a perfect record of the past. The challenges are as much psychological as they are physical. The constant, screaming wind, the unrelenting 24-hour daylight of the polar summer, and the sheer monotony of the white landscape can take a toll on even the most resilient individuals. There's a phenomenon often called Big Eye, where the endless day disrupts sleep patterns, leading to exhaustion and irritability. The isolation from loved ones is profound. Satellite phone calls are brief and precious, a fragile link to a world that feels increasingly distant. To combat this, teams develop their own rituals and traditions. They celebrate birthdays with makeshift cakes, hold weekly movie nights projected onto a sheet, and mark the halfway point of the expedition with a special dinner. These small acts of normalcy are vital anchors, reminders of humanity in a vast, inhuman landscape. But for all the hardship, these scientists will quickly tell you that the rewards are immeasurable, and they often arrive in moments of sheer, heart-stopping wonder. It might come during a brief lull in the wind, when the absolute silence of the ice sheet becomes a palpable, awe-inspiring presence. Or it might be the night the aurora australis erupts overhead, painting the entire sky in rippling curtains of green and purple. A light show so magnificent it makes the brutal cold feel insignificant. The ultimate reward, however, is the moment of discovery itself. There is no feeling quite like being present when a drill segment containing ice from 100,000 years ago is first hauled to the surface. The team gathers around, their breath pluming in the floodlights, as a researcher in thick gloves gently brushes away the frost. Seeing that pristine, bubbly ice, knowing it holds air that hasn't been breathed by any creature since the time of the Neanderthals, creates an electric sense of connection across the ages. It's a visceral, emotional punch that makes every frozen moment worthwhile. This pursuit is no longer the domain of a single type of explorer. The field has blossomed into a wonderfully diverse and international endeavor. Modern drilling projects are massive collaborations, bringing together experts from every corner of the globe. A single team might include a Japanese chemist specializing in gas analysis, a British engineer who designed the drill, a Brazilian scientist studying ancient pollen, and early career researchers from Kenya and Germany. This diversity of perspective is its own kind of strength. It ensures that the questions being asked of the ice are rich and varied, and that the resulting science benefits from a wealth of cultural and intellectual backgrounds. It shatters the old stereotype of the lone polar explorer, revealing a vibrant global community united by a shared passion for understanding our planet's story, one core at a time. For all the incredible secrets we've already pried from these frozen depths, some of the most profound questions remain tantalizingly out of reach, locked away in ice we have yet to drill or layers we cannot yet read with perfect clarity. These are the lingering mysteries that keep scientists awake at night and drive the next generation of expeditions. One of the biggest head-scratchers revolves around those dramatic Dansgaard-Easter events, the abrupt, massive warming spikes we see in the Greenland ice cores. We have a strong leading hypothesis that they were triggered by sudden shifts in the North Atlantic's ocean circulation, but the precise mechanism that could flip this planetary scale, switch on and off so rapidly, remains elusive. Finding older, high-resolution ice from a period with even more of these events could provide the missing clues, revealing the exact sequence of changes in ocean temperature and salinity that preceded each sudden jump, allowing us to finally build a complete model of this climatic hair trigger. Another grand puzzle involves pushing beyond the 800,000-year barrier to understand a fundamental shift in Earth's very rhythm. Before roughly 1.2 million years ago, evidence from ocean sediments suggests the planet's ice age cycles pulsed to a different beat, dominated by a 41,000-year cycle tied to the wobble in Earth's tilt. Then, for reasons we don't fully understand, the rhythm shifted to the deeper, 100,000-year beat we see in the more recent ice core record. This transition is the white whale of paleoclimatology. Did greenhouse gases play the same amplifying role in that earlier world? Was the change caused by a gradual cooling of the planet, a shift in ocean chemistry, or perhaps the slow grinding of continents altering ocean currents? Only by retrieving and analyzing atmospheric samples from that pivotal era, air trapped in ice over 1 million years old, can we hope to solve this mystery. The answers would fundamentally rewrite our understanding of how sensitive our climate system is to its various dials and knobs over the very long term. Beyond these grand cycles, there are smaller, yet equally intriguing, anomalies buried in the existing records that beg for an explanation. In several cores, researchers have identified sudden, short-lived spikes in methane concentrations that don't seem to correlate with any known warming event or volcanic eruption. What could cause such a rapid release of this potent greenhouse gas? Was it a massive belch of methane from melting permafrost or oceanic hydrates, a prehistoric warning of a feedback loop we fear today? Or could it have been a huge, singular event, like the catastrophic draining of a glacial lake that flooded and decomposed vast areas of vegetation? Higher resolution analysis of these specific layers, perhaps looking for specific isotopes of carbon that could fingerprint the methane source, might finally crack the case. The quest isn't just about older ice, it's also about clearer ice. Even within cores we already have, there are layers distorted by subtle folding or stretching that blur their chronological details. New analytical techniques like non-destructive 3D imaging with ultra-high-resolution CT scanners are acting like corrective lenses for these blurred pages. They may allow us to digitally unfold these layers, restoring their original sequence and revealing short-lived events or precise annual data that were previously smeared beyond recognition. This could help us pinpoint, for example, the exact year and duration of a volcanic winter caused by a super eruption, allowing historians to correlate it with specific years of famine and societal collapse recorded in ancient texts with unprecedented precision. These are not just academic exercises. The enigmas locked in the ice are directly relevant to the challenges we face today. Understanding the precise causes of past abrupt climate change is the best way to assess our own risk of triggering similar events in the future. Determining the full range of natural variability in greenhouse gas levels provides the essential baseline for measuring just how far outside the norm our current experiment with the atmosphere truly is. Each new core drilled, each new technological innovation in analysis, is like turning on a light in a dark, vast room of Earth's history. We can see the outlines of the furniture now, but the next steps will illuminate the corners, revealing details and objects we never knew were there. The frozen cliffs have given us a masterpiece of our planet's story, but the most thrilling chapters may still be waiting, frozen in time, daring us to come and read them. You might be listening to this and feeling that the story of these ice cores is something happening in distant, frozen labs, a narrative for scientists alone. But nothing could be further from the truth. This is a story that belongs to all of us, and there are so many tangible, exciting ways you can become a part of it yourself, moving from a fascinated observer to an active participant in this great discovery. You don't need a PhD or a Parker to start exploring. The journey can begin right from your own home. One of the most immediate and awe-inspiring ways to connect is by seeking out institutions that proudly display these frozen time capsules. Several major natural history museums, like the Smithsonian in Washington, D.C., or the American Museum of Natural History in New York, have incredible exhibits featuring actual segments of ice cores. There is a profound difference between seeing a picture of those trapped bubbles and standing in front of a real, millennia-old cylinder of ice, seeing the layers and imperfections with your own eyes. These exhibits often pair the physical core with interactive displays that let you virtually drill into the ice, analyze the gases, and see the climate data come to life. It's a powerful, tangible connection that makes the science feel immediate and real, a perfect starting point for curiosity. For those who prefer to explore from the comfort of their couch, a wealth of stunning documentaries have been made that take you directly to the ice. Films like Chasing Ice or the groundbreaking series Frozen Planet offer breathtaking cinematography that puts you right in the field with the scientists, feeling the biting wind and sharing the tension and triumph of a successful core extraction. For a deeper dive into the history and implications, the documentary Ice and the Sky tells the personal story of Claude Lorius, one of the founding giants of this field, and his lifelong quest to understand the climate secrets locked in Antarctica. These films do more than just inform. They inspire an emotional connection to the polar worlds and the people dedicating their lives to understanding them. And if you're hungry for even more detail, there are fantastic books that explore the topic, from the accessible science writing in Elizabeth Kolbert's The Sixth Extinction, which features ice core research, to more focused texts that chronicle the entire adventurous history of polar exploration and discovery. Perhaps the most engaging way to get involved is to actually roll up your sleeves and contribute to real scientific research through citizen science projects. Online platforms like Zooniverse host initiatives where anyone can help researchers by reviewing vast datasets of images. You could be tasked with counting dust particles in microscopic images of ice, or helping to identify annual layers in core scans from the comfort of your computer. Your eyes and your time become a valuable resource, helping professional scientists process information faster than they ever could alone. This isn't busy work, these are genuine contributions to ongoing research. By participating, you're not just learning about the process, you're actively advancing it, becoming one of the many people around the world helping to turn raw data into meaningful discovery. It's a fantastic way to gain a deeper appreciation for the meticulous work involved and to feel a direct sense of ownership in the scientific process. Your journey of engagement can also be a structured one through online education. Platforms like Coursera and edX offer courses on climate science, paleoclimatology, and even specific classes on the cryosphere taught by leading professors from universities around the world. These courses allow you to learn the fundamental principles at your own pace, often for free, giving you the vocabulary and context to understand the latest news and research with a critical and informed eye. This knowledge empowers you to have more meaningful conversations about climate change, cutting through the noise of misinformation and understanding the solid evidence that underpins our current understanding. Ultimately, the most powerful way every single person can engage with this science is by becoming an advocate for the preservation of these very archives and the stable climate they document. The research we've discussed doesn't happen in a vacuum. It's funded by government grants and supported by international cooperation. You can support non-profit organizations like the National Snow and Ice Data Center or Polar Bears International that work to communicate this science to the public and policymakers. You can use your voice to contact your elected representatives and emphasize the importance of funding this basic research. And on the most fundamental level, you can make choices in your own life that reduce your carbon footprint, and you can vote for leaders at every level of government who prioritize evidence-based climate policy. The ice cores show us that our atmosphere is a shared global heritage. By advocating for its protection, you are helping to ensure that the story they tell doesn't end with our chapter, but continues for millennia to come, a record of a generation that understood the past and chose to protect the future. And so this journey through deep time, locked within these silent, frozen cliffs, draws to a close, but the story they tell is far from over. It's a profound reminder that every breath we take today is part of a vast, interconnected tapestry woven over hundreds of thousands of winters, a direct link to the ancient skies that once enveloped woolly mammoths, early human migrations, and worlds long since vanished. These atmospheric fossils have done more than just satisfy scientific curiosity. They have fundamentally rewritten our relationship with the planet, offering irrefutable evidence that our climate is a dynamic, sensitive system, deeply responsive to the chemical composition of the air. They have taken us from theoretical models to a concrete, physical timeline, showing us the intimate dance between greenhouse gases and global temperature with a clarity that is both beautiful and, in our current moment, deeply sobering. This is not just history, it is a mirror reflecting the unprecedented nature of the changes we are now driving, and a warning etched in ice and air. The urgency this knowledge imparts cannot be overstated. These fragile archives are not merely records of the past, they are the very benchmarks we need to navigate the future. They provide the essential context that separates natural variability from human-caused disruption, allowing us to see the stark, vertical spike of modern carbon dioxide levels against the gentle, rhythmic waves of the past 800,000 years. This long-term perspective is our most powerful tool for building accurate climate models and setting tangible, meaningful targets for a stable planet. Yet, in a cruel twist of fate, the warming we have unleashed now threatens to destroy these very libraries before we have even finished reading them. The melting ice is not just a symbol of loss, it is an active erasure of Earth's memory, a permanent deletion of data we desperately need. This creates a dual imperative: to drastically reduce our emissions to protect the ice that remains, and to support the heroic, ongoing scientific efforts to extract and preserve these cores before they are lost forever. This isn't a story that ends with scientists in remote polar camps. It continues with every one of us. It calls for a collective appreciation for these fragile, frozen wonders and a renewed commitment to stewardship. You can be part of this story by seeking out knowledge, visiting museums with ice core exhibits, supporting research organizations, and most importantly, by adding your voice to the call for meaningful climate action. Share what you've learned here today, discuss it, and let it shape the choices you make and the leaders you support. These frozen cliffs have given us the most profound gift: the context to understand our present and the wisdom to choose a different path forward. They hold not just the keys to our past, but the maps to our future. If you've enjoyed this exploration into Earth's deepest mysteries, consider subscribing to continue the journey with us. We'd love to hear your thoughts in the comments below. What astonished you the most about these incredible time capsules? Thank